Hello and welcome back to Chopstick Maths. In this video, we shall be solving sum number 4 from exercise 3. Solve the differential equation x cube into e raised to x minus my square dx plus mxy dy is equal to 0. And let us call this as equation number 1. First of all, we will find out if this given equation is an exact differential equation or not. So let us compare this given differential equation with m dx plus n dy is equal to 0. Therefore, on comparing this with m dx plus n dy is equal to 0, we get m is equal to x cube into e raised to x minus my square and n equals to mxy. Now we'll have to differentiate m partially with respect to y, and we'll have to differentiate n partially with respect to x. And if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, then we can say that this given equation is an exact differential equation. So now let us proceed to differentiate partially with respect to y. Therefore, del m by del y is equal to del by del y of x cube into e raised to x minus m del by del y of y square. Now whenever you're differentiating partially with respect to y, you have to treat x as a constant. Therefore, del by del y of x cube into e raised to x is 0. m being a constant comes out, so this will be minus m del by del y of y square, and del by del y of y square is 2y. So del m by del y equals to 0 minus m into 2y. So del m by del y equals to minus 2my. Now n equals to mxy. So let us now partially differentiate n with respect to x. Therefore, del n by del x equals to my del by del x of x. Now m is a constant, and whenever you are differentiating partially with respect to x, you have to treat y as a constant. So m and y comes out, so del n by del x is my del by del x of x. Now del by del x of x equals to 1. So del n by del x is my into 1. So del n by del x equals to my. Now we can see that del m by del y is not equal to del n by del x. Therefore, this given equation is not an exact differential equation. Now, we'll have to find a suitable integrating factor such that when we multiply this given differential equation with the integrating factor, then this particular differential equation will be reduced to an exact differential equation. Now, if del m by del y minus del n by del x upon n is a function of x only, say f of x, then the integrating factor is equal to e raised to integral of f of x dx. Now del m by del y equals to minus 2my and del n by del x equals to my. Therefore, del m by del y minus del n by del x upon n will be equal to minus 2my minus my upon, and n is mxy, which will be equal to minus 3my upon myx. Now here my will cancel in the numerator and denominator. Therefore, this would be equal to minus 3 by x. Therefore, del m by del y minus del n by del x upon n equals to minus 3 by x. That is, it is a function of x only, and we call it as f of x. Therefore, the integrating factor is e raised to integral f of x dx. So let us now substitute f of x equals to minus 3 by x. So the integrating factor would be e raised to integral minus 3 by x dx. Now since 3 is a constant, we can pull minus 3 outside the integral sign. So the integrating factor is equal to e raised to minus 3 integral 1 upon x dx. And integral 1 upon x dx equals to log x to the base e. So the integrating factor is equal to e raised to minus 3 log x to the base e. Now using this particular property of log, that is m log a to the base e is equal to log a raised to m to the base e. So we can now write the integrating factor as e raised to log x raised to minus 3 to the base e. Now using the second property of logarithm, which is e raised to log f of x to the base e is equal to f of x. So we can now write e raised to log x raised to minus 3 to the base e is equal to x raised to minus 3. So the integrating factor is 1 upon x cube. Now multiplying equation 1 by the integrating factor 1 upon x cube, we get 1 upon x cube into bracket x cube into e raised to x minus my square dx plus 1 upon x cube into mxy dy equals to 0. Now when we multiply 1 upon x cube with the first term, x cube gets cancelled in the numerator and denominator, and what is left is e raised to x. And when we multiply 1 upon x cube with the second term, my square, we get minus my square upon x cube dx plus, here x would get cancelled in the numerator and denominator, and what will be left is my upon x square dy is equal to 0. Now let us call this as equation 4. Now this equation 4 is an exact differential equation. Now the solution to this exact differential equation is integral m dx keeping y as constant plus integral n dy and integrating only those terms from n which are free of x equals to c. Now this would be integral e raised to x dx minus m is a constant and we have to keep y also as a constant. So minus my square would come out integral 1 upon x cube dx plus we have to integrate only those terms from n which are free of x. Now here n has one term only, which is my square upon x square. So here there is an x in the n term. So we should neglect this particular term. So this would be plus integral 0 dy is equal to c dash. Now we can write this as integral e raised to x dx minus my square integral x raised to minus 3 dx is equal to c dash. Now integral of e raised to x dx is e raised to x minus my square, and integral of x raised to minus 3 dx, we can integrate this using the formula integral x raised to n dx is equal to x raised to n plus 1 upon n plus 1 plus c. Therefore integral of x raised to minus 3 dx is x raised to minus 2 upon minus 2, which is equal to c dash. Now we can write this as e raised to x plus my square upon 2 x square, which is equal to c dash. Now taking the LCM, we can write 2x square e raised to x plus my square upon 2x square is equal to c dash. And now this can be written as 2x square e raised to x plus my square equals to 2c dash x square. And 2c dash can be now written as another constant c. So this can be now written as 2x square e raised to x plus my square equals to cx square. So this is the solution for the given differential equation. Thank you very much for watching the video. See you in the next video. Bye.